Hi everyone, welcome to lesson 3. I'll start again. Hi everyone, welcome to lesson 3 of theme 3, GCSE Geography. So last lesson we were looking at destructive boundaries that destroy crust. Today we're going to look at constructive boundaries that create crust. And we're going to do a similar approach to how we did the destructive boundaries. We're going to explain the processes that happen, can't talk today, and then identify and explain the main features and hazards that are created at this type of plate boundary. So pause the video here a moment, go ahead and write down the title and we'll get going. Okay, so if I just come out of here a moment, I'm going to show you a video clip on YouTube that recaps convection currents, destructive boundaries and introduces constructive boundaries.
It happens because hot rock rises, heated by the Earth's core. Near the surface, the rock spreads in two directions and goes sideways. It begins to lose heat. Eventually, the much cooler rock sinks back down.
Okay, so what you've got here is the destructive boundary we were looking at last lesson, where crust is sinking and being destroyed. It's melting in the mantle. And what's happening here is crust is being created, where magma rises in the gap, and you get a small underwater eruption, and where that hot liquid rock touches freezing cold ocean, it cools and turns solid to create new rock and form new crust.
Through this spreading process, the Earth's crust is very slowly dragged apart, and it's this that ultimately causes the continents to move. Where the plates collide, the rock on the seafloor containing carbon from the dead plankton is carried deep into the earth. As it descends, this layer of rock is heated, so the rock melts, releasing carbon dioxide. And gas is returned back into the atmosphere during an eruption. The remarkable cycle is complete.
I thought that video went on to I thought that video went on to constructive boundaries. It recaps destructive anyway. So we'll just roll with it. So a constructive boundary, this is how it works. This is a very basic animation, but you've got the upwelling here, where convection currents are moving away from each other. It pulls the crust apart and magma rises in the gap. When that boiling hot liquid magma touches freezing cold ocean, it causes it to solidify and create new rock. It creates new crust. Now you sometimes ask me, why doesn't the water go into the earth? Kind of what happens on the seafloor where this is happening? The pressure and heat of the magma escaping is greater than the pressure and low temperature of the water trying to get in. So magma always comes out and and solidifies rather than water going in and turning to steam. Now that's not to say that where the magma is erupting and you get small seafloor volcanic eruptions that there isn't a lot of steam and boiling of the ocean water going on, but it tends to be the magma comes out rather than the water goes in. Okay, so again, you have, similar to last lesson, in the lesson folder for this, you have got a sheet like this. Now, if you're able to print this off A3, great at home. Otherwise, we can just work in subheadings again. So the first thing we're going to do is write an explanation of how a constructive boundary actually works. Sometimes it's called divergent. To diverge means to move away. Okay, so sometimes it's called divergent instead of constructive. Just be aware of that. So that first box, or put that first subheading, okay. I'm having a mare with technology this morning. Here's a slightly more complex version of the diagram. So you can see the convection currents are moving away from each other, and that pulls the plates on top away from each other, and it creates a mid-ocean ridge. Where this magma is rising, it pushes the edge of the plates up slightly, and you get underwater volcanic eruptions happening all the way along this ridge that create new crust. Okay, so convection currents rise and separate, pulling the crust apart. Under the sea, this is called seafloor spreading. The majority of constructive boundaries happen under the ocean. There's one exception that happens under a continent. Well, There's one main exception that happens under a continent. When a constructive boundary happens under the land, it creates a rift valley. A rift is like a split or a tear. It literally rips the continent apart, and in the gap, the rock kind of falls and collapses into the gap, making a massive valley. I'll show you pictures later on. But under the ocean, it's called seafloor spreading because it literally spreads the seafloor apart. Magma then rises in that gap, and when it is erupted, it hardens when it touches the cold ocean to form new crust, creating a mid-ocean ridge. Volcanic islands can form if the eruptions along that mid-ocean ridge continue either enough times or continually at one time for long enough. Then the cooled rock will build up and build up and build up, forming an underwater volcano, and eventually it might pop out the top of the sea, at the top of what's called a mantle plume. That's how islands like Iceland have been formed. They are the top, really, of essentially underwater volcanoes that have erupted from a mid-ocean ridge due to seafloor spreading at a constructive plate boundary, and it's continued for long enough that that volcano pops out the top of the ocean. Iceland is actually the top of a mantle plume of about 9 volcanoes across the island. So pause the video here a moment, go ahead and write this down into that box 1 or under your subheading. Okay, the next thing we're going to look at is how it creates, let's take a look at the sheet, how it creates certain features. Okay, so we're going to go for mid-ocean ridges first, and then rift valleys and volcanic hotspots. Now, in terms of hazards at constructive plate boundaries, you don't get all 3 like you do at destructive boundaries. You won't get tsunamis here. Any earthquakes are more minor. You mainly just get volcanic eruptions. Okay, so we'll talk about the mid-ocean ridge first. So I want you to redraw the diagram from box 1 and annotate it to explain how a mid-ocean ridge forms. So again, if you've got the sheet, great. Otherwise, put down a subheading. And I'd like you to do your best to draw this and annotate it with things like convection currents rise in the mantle and push the edge of the oceanic crust upward slightly. As the convection current pulls the 2 plates away from each other, this creates a constructive plate boundary. The pulling apart and the pushing up create a ridge on the sea floor. This is known as a mid-ocean ridge. So subheading, or on the sheet, draw this, re-listen to what I just said, and annotate it as best you can. These 2 words here, lithosphere and asthenosphere, the mantle and crust is actually split into more layers than we talk about at GCSE level. You do not need to know these words. All right, they just happen to be on this diagram, so don't stress about those. So pause the video here a moment, go ahead and make your own copy and annotate this diagram. Okay, so I said usually constructive boundaries happen under the ocean. And it forms, a mid-ocean ridge like this. Occasionally, they happen under a continent. The best example is in this area of Africa. It's called the Great African Rift Valley. What's happening is there is a constructive boundary running here. The convection currents are coming this way and this way, and it's ripping the continent of Africa apart here. Over time, this area of Africa, known as the Horn of Africa, will probably actually tear away from the main continent, and water will flood into the gap to create a new sea. And eventually, as the Rift Valley continues to widen and widen and widen, more water will flood in, and it will eventually become a small ocean until it maybe gets bigger and bigger and becomes a large ocean. It's exactly the same way that the Atlantic Ocean was created, because as we mentioned, Pangea, all the continents used to be joined together. South America and Africa and Europe and North America have since pulled apart, and the water has rushed in to fill the gap. And that's what made the Atlantic Ocean. We're getting about 2 centimetres further away from America every year. The Atlantic Ocean is technically widening because of seafloor spreading. And the Rift Valley will continue to widen. You can see it here. So here's one side, which will be running down that edge there. And then just off the photo here, here's the other side, which will be running down this edge here. So what sort of happened, if you can visualise this, is the convection currents underneath tear the continent apart above it. And to start with, the land sort of breaks and falls down into the gap, creating a huge rift valley that at the moment in Africa is dry. You can see where it's sort of tearing and ripping here in like a stepped formation, like you can see here. Over time, as this widens, some water will flood in, either from this area, the Red Sea, or maybe from the Indian Ocean, from here, will flood in there or there. And it will form a new baby sea. An example of this in real life is the Red Sea. Eventually, as it spreads further and further and more water floods into the gap, you get a more established ocean. So what I'd like you to do is either, again, on your sheet, or if you don't have the sheet printed out, do your best to make a copy of this diagram and annotate it around the edges, please. Okay? So convection currents under a continent begin to tear the continent apart, and the land falls down to fill the gap, to create a rift valley. Over time, as the rift valley widens, water will begin to fill the gap to create a new ocean basin. As time goes on even more, the rift valley widens further and more water floods in, and eventually you end up with a mature ocean, like the Atlantic is today. So re-listen to that, draw and annotate, or on your sheet just annotate to explain how rift valleys are formed. Okay, so the last thing to discuss, the last feature, is volcanic hotspots. Now, in the very first lesson, we established that almost all volcanic eruptions and earthquakes happen along plate boundaries, but I did mention that there are some exceptions. You get intraplate within plate earthquakes, sometimes due to pressure around the edges, and you sometimes get intraplate volcanoes as well. So we're nowhere near a plate boundary, and yet we've got a volcano. What's happening here? If you try to imagine holding a piece of paper over a candle, and you move that piece of paper over the candle really slowly, at some points the candle will burn through the piece of paper. That's like what is happening in some parts of the mantle as the crust or a piece of plate moves over the top of it. What can sometimes happen in the mantle is you get an extra hot bit, okay, called a mantle plume. And what that will do, as the tectonic plate above it passes over the top, it will burn through and create volcanic eruptions. All right? Now, over time, what will happen, as the plate passes over the top of the hotspot of the mantle plume, it will create a volcano, and then that plate will move, and that volcano gets carried off the hotspot, and it goes extinct. It won't erupt again. And the plate keeps moving, and what you end up with is like a trace that if you reverse it, you can tell the direction of the plate. And what happens over time is, so Hawaii is a perfect example of a hotspot volcano. The main island of Hawaii still has active volcanoes on it at the moment. It's over the hotspot right now. The other smaller islands of Hawaii used to be over the hotspot, but the plate has since carried them off. So these are now extinct volcanic islands. And what's happened here, these are old volcanic islands that, because they're not over the hotspot anymore, they're not actively erupting, and so coastal erosion by the sea has taken over and worn them down until they're called what are known as seamounts. All right? So I thought I had an animation. Sometimes a volcano will form away from a plate boundary. A thermal plume or hotspot rises underneath the plate, and the heat from the plume causes an eruption on the seafloor. As this happens repeatedly over time, eventually it'll pop out the top of the sea, and it creates a volcanic island. What then happens, though, is the plate keeps moving over the top of the hotspot, and it carries the volcano off the hotspot, and it becomes extinct. It stops erupting. And over time, as those islands are carried further away from the hotspot, they cool and contract, and coastal erosion wears them away until they disappear beneath the ocean surface, and they're then known as seamounts. So pause the video here a moment and use these sentences. You can summarise it further if you're able to, or you can just copy it word for word, I don't mind. But put this down to explain how seamounts and volcanic island arcs are created. I thought there was an animation. Here we go. So this explains hotspots and volcanic islands.
Not all volcanoes form at plate boundaries. Some form instead in the interior of a plate, where geologists call them hotspot volcanoes or simply hotspots. One explanation of such activity is the presence of a mantle plume, a regionally restricted column of hot rock rising inside the asthenosphere. When it reaches the base of the lithosphere, the rock partially melts, sending intrusions of magma upwards into the plate. Some of this magma erupts to form active underwater volcanoes, or, if activity is sustained, an active volcanic island. An entire chain of such islands forms because the plate carrying the volcanoes moves across the stationary hotspot inside the asthenosphere. This movement slowly carries the active volcano off the mantle plume, causing it to go extinct. A new island grows in its place over the plume. When the plate motion changes, so does the direction of the volcanic island chain. The inactive older islands cool and subside with distance to the heat source and experience significant erosion. With time, former hotspot islands turn into smaller shallow islands and ultimately become underwater seamounts.
Okay, so that brings us to the end of lesson 3. Well done. What we're going to start looking at next lesson is focusing more specifically on volcanoes themselves, because there's 3 different types: shield, strato and cinder cone, and we're going to look at how the eruptions and the size and the shape differ between those 3 main types, and we're going to look at lava tubes and geysers and other features of volcanic landscapes. So I'll see you soon for lesson 4.